Happy Friday to y'all. Okay. So last class, that'll hopefully, that's not gonna work. I'm just gonna keep talking while I continue to set stuff. So last class we finished up capacitors and resistivity. And settle down, everyone. Don't worry, I'm gonna give you plenty of opportunities to talk to each other. Okay, should hopefully be set up now. If not, I'll make it work. There we go. Okay, so last class we finished off capacitors. I gave you a couple problems on them. The quiz for them is this, so a couple problems on capacitors. We talked about resistivity. That was kind of the big thing we talked about, which is just the property of a material to resist the flow of electrons. This is purely based on what material you have, whether it's whatever element or alloy. It doesn't need to be a pure element. It could be some combination of a bunch of things. And even, for instance, carbon. You see here there's a range of resistivities, and that depends on how it's structured. So if you have diamond versus graphite in a pencil, the temperature dependence of that at room temperature you get these values, that there's some temperature coefficient, and you can get the final resistivity at some given temperature by just plugging that in. The last thing I kind of quickly tried to say to you all, and I mostly got through, that when you're actually in the real world doing this in engineering, the type of material you use is not just based on, oh, this has the lowest resistivity, so that's the one I'm going to choose. No, you also have to factor in cost, you have to factor in how it's going to behave in the environment it's in, you have to factor in if it's going to react to whatever thing. So for the easy examples, if I use iron as a wire, it's going to turn into rust, and rust is not very conductive, so you end up not having a good thing, whereas gold is non-reactive, and so that's why most of your fine circuitry in your devices is gold for that very reason. There's even another level, which I forgot to say, which is the interface of two materials also matters. So in engineering, especially once you get to devices like the transistors in your phone, really small levels, say I have gold and that interface is then with, let's just pick something random, copper, whatever. That interface can actually matter, and you may choose a different material so that the electrons can flow from one material better to the other. Sometimes we just think, oh, it's all metal, so it's going to flow easily from one to the other, but actually when you have two different materials interacting with each other, that can be a barrier. That's something called, there's a work function you look at. Electro engineers, maybe you'll get to that, I don't actually know. Physics, if you do condensed matter research, you will. All right, so that's that. Today, we are going to start moving to current resistance. I will tell you from this class moving forward, this will not be on the next test. So it won't be on the test coming up. It will be on the test after that. So we have the things that will be on the next test. I guess I'll spend some time just quickly talking about this. Is everything we've covered up to this point. So electric fields, electric forces, charges, voltage, potential energy, and capacitors and resistivity. All of those will be on your test, so basically everything you've been quizzed on. The reason this is not going to be on your test, even though we're covering it before the test, is because we don't have time to get the quiz. So I will never test you on something I haven't given you a quiz beforehand on. So the quiz for currents and DC circuits isn't due until February 28th, after the test. So even though we're covering it now, I want to give you a chance to actually check your understanding, and that's why that's the case. So we're still going to cover it now, but the quiz won't be till afterwards, so this is just how things end up working out. All that to say, please do still pay attention and engage your brain as we're doing this. The concepts that we're going to be using here will be concepts that you'll need for the test anyway. All of the things we cover in this class are going to build on previous information. For the most part. Once we get to magnetic fields, we'll kind of restart a bit. But at least everything in circuits is going to build upon everything you've talked about already. That's how physics works. So, still important, and obviously you're going to get tested on it eventually, so still important there. Okay. So, what do we, as I said, if it's building on, what's it actually building on? These are the important things that we've covered thus far, and these are the important things you need to remember. Let me just check that this is actually recording. All right, cool. Reminder that it is electrons which move in a circuit. So if we ever say current is moving or ever say charges are moving, it's always electrons. The reason being, if it's protons moving, that means it's hydrogen atoms moving. You do not have hydrogen atoms moving in your wires. Okay, so whenever we talk about current, well, we'll get to what current is, but whenever we talk about moving charges, what is literally happening is electrons are moving. Voltage, we're going to be using that, obviously, because batteries have voltage. So clearly, hopefully that seems obvious that we're going to need that. Electric potential energy, and that one we mainly need, as I've mentioned a bunch of times, things move from higher energy to lower potential energy. So higher potential energy to lower potential energy. So this explains why why current flows the way it does. So all of these fundamental concepts help us to actually understand everything I'm going to cover. What are we going to actually cover in this? We're going to identify what current is, how batteries generate current, and when I say how batteries generate current, more so that potential difference, not the chemical reaction. That's a chemistry thing. If you're interested in it, please look it up. I don't know the details on it personally, exactly all the chemistry behind it, but it is basically just separating charges. Identifying what resistance is, talked about that a little bit already. What current, voltage, and resistance and the relationship, which is Ohm's law. And then power. Applying the definition of power for circuit elements. Power is basically the energy lost per second. So the energy consumed, because as these charges flow, you want to actually do something useful with them, and that's what power is going to tell us, is how much energy you get out per second. All right, here is the definition of current. The unit of current is an ampere. That was just, again, someone else discovered it, and so ampere gets named after him. Here's the challenge. This should not be. Unit of current is A. 5 amps. But when you see it in equations, it's going to be I. So this is one of those, unfortunately, the unit doesn't match up with the variable. So when you use it in equations, it's going to be I. But if you ever report the unit, it's going to be like 30 amps. So example, 30 amps. There you go. I'll decide at some point. But the basic definition is it is how much positive charge is moving through a cross-sectional area per time. This is immediately, maybe we're going to be like, why are you saying positive charge moving if you just told me that electrons are the one moving? And that's just because someone decided this at some point, and that's what we've stuck with ever since. It is not accurate to what is literally happening, but it is what, when they experimentally observe this, they decide to say that, oh, we'll have positive charge moving. They eventually realize it's actually electrons moving. But all you have to do and kind of think in your brain is whenever you think of current, if you actually physically want to think of what's happening, it's charges moving the other way, negative charges moving the other way, which is effectively the same thing as positive charges moving that way. Physically, positive charges aren't moving, but we can use that conceptual trick to just, it still works out the same. Again, it's frustrating, it's a little weird, but I just really want to hammer home current is positive charge moving, but that is not literally what's happening. In the real world, it's electrons moving. Okay. And it's through a cross-sectional area. It's a rate of flow is basically all current is, which matches up with the word current, like water current. It's how much charge moves through the thing, through some cross-sectional area in some unit of time. So you can see here's my nice little derivative, the amount of charge over some time. So now you get to test that idea if it's the amount of charge that moves through something over some time. See if you all can translate that to math. Get your clickers out. You got a few seconds because I don't even have it opened yet. All right. How much current flows through a wire if 30 coulombs of charge passes through it in 2 minutes? Make certain you convert everything to base units. All right, good question. What are the base units for time? There we go. No, it's always a good question to ask. What are the base units? Because mass is the one weird one, kilograms instead of grams. I don't know why, someone decided at some point. All right, gonna give y'all like 5 more seconds. So 5, 4, 3, 2, 1. All right. There you go. So real quick, if I just said that current equals dq dt, you can always kind of write these things on a more macro level as delta q delta t equals 30 divided by 120 seconds. There you go. Equals 1/4 amps, which is there. Fantastic. Real simple. So it's a rate of flow. In this case, it was just from beginning to end. But as we go on, cross-sectional area, we're going to need to consider that. All right, I'll leave this up for just a couple seconds. Okay. All right, now my conceptual question, you all spend some time thinking about this. Imagine I had a table with a bunch of balls on it. How would I easily make them all roll in one direction at the same time? So I want them all to start rolling at the same moment. Spend some time, think about it. How would you do that? All right, who has some ideas? Tilt the table. There you go. This table over here had a bunch of balls on it. Lift up the table, they're all going to start rolling at the same moment. The reason I am bringing up this example, you may be like, what does this have to do with electricity? What does this have to do with current? When you are tilting the table, when I tilt the table, what I'm effectively doing is providing a difference in potential energy. When it was flat, the potential energy was the same at every single point because the height was the same. Now, the potential energy at every single point is going to be greater than the one to the right of it because there's a height difference. So this potential, we'll just call this potential energy 1, potential energy 2, potential energy 1 greater than potential energy 2. Things go to lower potential energy. Now we can convey that with a wire. In a wire, there are electrons, free electrons just sitting around, floating around in the thing. That's what conductors have, that sea of electrons. That's what makes conductors special. Electrons that are just kind of randomly floating around such that the net movement is 0. The second I put a potential difference, so if I call this in V1, we'll just call this V1. V1 equals 0. Call the potential on this end 0. Call the potential on this end 10. That means that there's some linear, and we'll just say like at every point in between. Say at this point it's 5. All I'm trying to emphasize here is that the potential is changing linearly. Potential energy is equal to Q times V. These are electrons, so it's negative 1.602. At this point, their energy equals negative 1.602 times 10 times 10. All this to say, this is a negative number is a smaller number than 0. So if I call this side A and I call this side B, the energy, I'm running out of room. Energy A greater than energy of B, the electrons are going to start moving because they are going to move to the area of lower energy. This is how you make current. You put a potential difference, and a potential difference is effectively the same thing as tilting your table. The electrons are all in the wire already. It's not that you're injecting electrons in, it's that they're already there. I then tilt the wire, I add that potential difference, that results in a potential energy difference, and they flow from the low voltage to the high voltage. To translate this into current, which remember current is positive charge moving, if I have electrons moving from left to right, that is effectively the same thing as current moving from right to left. If current is positive charge moving, then we imagine it's the opposite way that the electrons are moving. So current flows from high voltage to low voltage. In reality, it's electrons moving the other way, from low voltage to high voltage. But that's it. That is why current flows in a wire. You put a battery there, you introduced a place of higher potential energy and a place of lower potential energy. That's the mystery explained. How does electricity work? There you go. Now you all can explain this to anyone. Maybe you understood this already, maybe not. This is kind of what we're going to be working with for the next 2 weeks. This idea and how it translates to actual circuits and the math behind it. Any questions on this? I want to give some space here because this is like the fundamental, how electricity flows. All right. So there you go. Just kind of showed that already. Electrons are going to move from higher to lower energy. Current flows in the opposite direction. So same thing that I already said. I said this before as well. So as the electrons are moving, they don't actually end up moving in a straight path. If they did, their velocity would end up being very high. So if you just did the simple math of like change in potential energy equals change in kinetic energy, that is assuming that there's no collisions, but there is collisions. So this is where if you have 5 amps of current, an amp of current is a lot of current. Always good to have a sense of magnitude. If you have 1 amp of current, that's a lot. Most devices don't take that much. If you try to put 1 amp through a lot of devices, they'll end up breaking. And we'll explain why they end up breaking. So if I have 5 amps, which is a lot of current, if you do a bunch of calculations, which we're not going to do in this class, you end up getting a drift velocity that's 7.35 times 10 to the minus 4 meters per second. Very, very slow. So it's a very slow velocity. And this is why I really kind of wanted to emphasize that in the wire there's electrons everywhere. Because if your assumption was that a battery is pushing in new electrons into an empty pipe, it would take a very long time for the electrons to go from one end of the battery all the way to the other. And that would mean that if it was an empty pipe that I'm adding stuff into, that would mean when you flip the light switch, that it would take like 30 minutes for your light to turn on. So it just doesn't make sense then. So they're always in there. The voltage though, it sees that when you flip the light switch, you close the circuit, it sees the difference, it sees that super quick. That's like on the order of the speed of light. When it generates an electric field, it sees that electric field super quick. That information travels very quickly, and so the electrons in the light bulb itself see that almost instantly. All right, we talked about resistivity. A lot of this can be repeat, already seen that. We talked about resistance, so some of these are repeat slides, but I put them in here again just because they connect so strongly. All right, so this is kind of a nice little summary. Resistivity, what we talked about, is a function of the material type and temperature, whereas resistance, which is now what we're going to emphasize a bit more, depends upon what material you use, how long the wire is, and the cross-sectional area. And we saw that in the last one, so it's both a geometric and material property. So you can see that in the previous slide. We showed this last time. Resistance equals resistivity, which is based on whatever material it is, times how long your wire is. The longer it is, the harder it is to push current through that. And divided by the area, the bigger your wire is, the wider it is, the easier it is for electrons to flow. Because really the actual reason is just you have more of them. You have more electrons, so as you put that potential, you get more of them flowing at once. That's where that area 1 comes from. And current is determined per cross-sectional area, so yeah. Pretty much what you're going to see when you see a resistor. I didn't have time for this last class, so I'm going to talk about it real quick. I'm never going to ask you questions to identify what resistor is which, but I at least wanted you to see this, because you're going to need to know this in your labs if you haven't already. And if you're working with any circuits at any point, you need to know how to read a resistor. This is not physics, this is, I don't know what you call it, engineering. This is how we've decided to label these things. So the way you read a resistor is there's going to be multiple bands. And depending on your resistor, you may have 5 bands, you may have 4. It still works the exact same way. But basically the first digit is going to be defined by the band on the left. And then the second digit is the band in the middle. Then you have your multiplier, and then you have your tolerance. So that sounds really obscure. What does it mean by first digit, second digit? Let me give you an example. This one is red, black, green. So you have this table, and this table tells you the number that corresponds to the color. So the red, we look at our table. Red is 2. All right? Then we look at black. Black is 0. Then we have the multiplier, which is green. So we find green and its tolerance to it. So in this case, silver is going to be plus or minus 10%. So whatever this, so 20 times 10 to the 5, your resistance is going to be plus or minus 20% of that. So multiply it by 1.2 or by 0.8. It's going to be somewhere between those values. It's not perfect. How you determine which end is left or right? Because I gave you like this, but if you had flipped it upside the other way, the silver would be first. Silver or gold will always be your last one. So that's how you determine which direction to read it in. Silver or gold is the last thing that's always tolerant. Silver and gold is not in this list. So there you go. You all will get plenty of practice in your labs. You're going to have plenty of practice doing this in life, especially if you're electrical engineering. It's ohms. But that's how you do it. And this is pretty much how all resistors are labeled. Little unfortunate, if you're colorblind, it's not very accessible, which sucks. But yeah, so probably a better way we could do it, but for now, this is how it is. One thing I wanted to emphasize, so this is what a resistor looks like. If you wanted to add specifically, you're like, oh, I need to add a resistance of 10 ohms to my circuit, you would find the resistor. Sometimes you just need to add a resistance. But everything actually has resistance. Just a simple wire in your circuit technically has a resistance. That resistance may be negligible compared to everything else, but it technically has one. A light bulb has a resistance. Any element, literally anything, if electrons have to flow through it, they are going to be, the material is going to impede the movement of electrons, therefore it's resisting it, has resistance. So in our class, we're basically going to consider discrete resistors in our circuits. I'll show you examples of what that looks like. But this is important to know when you're actually doing engineering, everything has resistance, and sometimes you need to account for that, depending on those values. Okay. Whew. I apologize. Because it's a lot of new stuff, unfortunately, it's a lot of me talking. Don't worry, there's the next question. You're going to have to actually do some math, talk to each other. But Ohm's law relates that if I apply a potential difference, if I put that battery in a circuit and I have a resistor in a circuit, this lets me calculate the current that flows through. This allows me to figure out how many electrons are flowing through my circuit. Well, how much positive charge is flowing through. Technically, as electrons. Really handy, really simple relationship, super nice. V equals IR. If you have a single resistor, you literally would just find, so if I had a 12 volt battery and a 6 ohm resistor, 12 divided by 6, current is 2. Way easier than calculating the number of electrons that flow through your circuit. No one's doing that. And the way you'd measure this, and I keep saying I'm going to talk more about this. We need to cover a few more topics to determine how you would actually physically measure that. But a voltmeter is what you use to measure the voltage across an element, ammeter. And how you set these up matter. You've already had to do that in class. We'll talk about why you have to set them up certain ways. And here's a nice graph where you can see as current goes up, voltage goes up, and you get this linear relationship, which is resistance. So for instance, say you wanted to calculate the resistance of some element. If you measured the voltage, you measured the current, you get this relationship. You could either get the line of it, or you can literally just pick any point and calculate it. Super simple. All right. This one's kind of funky, but I'm just going to kind of quickly tell you the answer to this one. Because I didn't quite give you enough. No, never mind. Go ahead and try. I'll tell you information. I'm not going to penalize you too much depending on what the answers I get. So this question is, shown below are the results of an experiment where 4 devices are connected across a variable voltage source. That just means I can change the voltage. That allowed me to get all these measurements. To get these measurements, I had to change the voltage. The voltage is increased and the current is measured. Which device, if any, is an ohmic device, aka obeys Ohm's law, which just means that V equals IR. What kind of relationship is this? Is it linear? Is it exponential? Is it logarithmic? As I increase voltage linearly, should current increase linearly or should it increase exponentially or whatever? There's just some math practice basically. And the reason this is important is because not all devices actually follow this ohmic relationship across all values. All right, give you all like 5 more seconds. So 5, 4, 3, 2, 1. All right. It's B. There you go. Straight line. You already saw in the last one. Hopefully that's pretty simple. The reason this question is interesting is because it turns out that as you increase the voltage and subsequently the current, you will actually at some point start to get more of like A, where it starts to like taper off. And the reason is that as you increase the current, eventually it actually so as you increase the current, you're pushing more electrons through it. As you're pushing more electrons through it, you are increasing the number of collisions that are happening, because electrons are literally going through it and bouncing off of things. As you're doing that, you increase the temperature. What happens when you increase the temperature? Resistivity increases. Well, resistivity increases, resistance increases. So you no longer get like this flat line, so at some high temperature, the current will actually start to decrease. And this is actually what your fuse does. As you are applying a voltage, at some point it gets so hot that a fuse will break. Fuses are specifically designed so that at a certain current, they reach a certain temperature. At that certain temperature, the material melts. It melts, your circuit breaks, it protects all the other equipment, because it's much cheaper to replace a 20-cent fuse than it is to replace a $1,000 whatever it's connected to. So, everything we're going to talk about is going to follow this, but in the real world, there's some like actual uses and benefits to it not following this. V will always equal IR. It just may not increase linearly. At every point, V will equal IR. So even on this graph here, this A, even though this isn't ohmic, this is still a true thing that this could be a device, and I can measure the voltage, I can measure the current, and I can calculate the resistance at that exact spot. That will always be true, but we may not be able to predict the next value by just saying it's linear. So it's not being ohmic. It's not obeying that linear relationship. All right. Another quick one. I got a battery. I got a resistor. Oh, I want to clarify this. This is how we're going to show batteries from now on. You got a short end and a long end. The long end is the positive terminal and the short end is the negative terminal. It's just really compact. This is what a resistor looks like. There's no directionality to resistors. Doesn't matter which way you put it. You can flip it either way. It's going to still behave the exact same way. Batteries do matter which way you face them. It's going to affect which way current flows. So yeah, what is the current flowing through the resistor in the following circuit? 5-volt battery, 15 ohm resistor. Real straightforward questions. All right, gonna close out in 3 seconds, pretty much everyone. So 3, 2, 1. All right. So here's the trick to this one. There's kind of an assumption here that I want to clarify that maybe you didn't even realize you were doing. This is kind of like, remember when we had the battery and we had the capacitor, and we said if the capacitor was the only thing in the circuit, it got the same voltage as the battery? That's the same thing here. If this is my battery, it basically means, to translate this, we say this side is 5 volts and this side is 0 volts. At every point on this side of the resistor, it is 5 volts. Once I get to the other end of the resistor, and so same thing here, and this is because we are saying that the wire has 0 resistance. It's not true in the real world, but whenever we do these problems, you can make that assumption, wire 0 resistance. Once it hits the resistor, there is a voltage drop of 5 volts. because it went from 5 to 0. Because of that, the voltage drop across the resistor equals the current through that resistor times R. So you all were actually doing more than you realized when doing this problem, but this is basically what's happening. So 5 volts equals I times 15 ohms. So you get that I equals 5 divided by 15 equals 1 over 3 amps. The reason I wanted to clarify, so again, pretty much all you got this right. The reason I wanted to clarify this whole voltage continuing all the way to here and that it's voltage across the battery that matters is because eventually, basically, after we finish these slides and move on to the next ones, we're going to start considering circuits that have more than one resistor. Amazing. In the real world, not many circuits are just literally one resistor and a battery. But we start somewhere. So say this is my circuit. I now have 2 resistors. So this one's R1, this one's R2. Same rule, if it's a 5-volt battery, it's going to be 5 here, 5 here, 5 here. But now it's going to be some unknown value here. And then if we said it's 5 there, it's got to be 0 here. 0 volts here, 0 volts here, 0 volts here. So the voltage drop across this one is 5 volts minus that mystery number. And the one over here is that mystery number minus 0 volts. We're going to later talk about how you actually end up reconciling that mystery number thing. We're going to do that. But I just wanted to clarify that that's the process you're actually doing when doing these problems. So for now, don't worry about figuring out how to solve this one. We'll talk about that next time. Looks worse than it is. But the reason we can do this one so simply is because it was 1 resistor, 1 battery. More resistors, more complicated. All right. Very last thing, basically, in this is I told you all we're going to talk about the power, which is the energy dissipated. So the amount of energy lost or gained by a device per second. When I use the word lost, that is usually going to be light, heat, sound. When I say gained, that may mean it's stored in something or used for something else. It all depends on what the unit of thing is. But just to clarify, energy is never destroyed, it's just converted from one thing to another. We generally say heat, light, or sound is lost energy because you're not going to be able to get that back very easily unless you put it like more or something. Anywho, energy, power is the change in energy over time. Well, what's energy? What's potential energy? It's just Q times V. We've covered that. And then the one step here that you have to do is, well, V is constant, then it's dQ dt, and dQ dt is I. There you go, you derived it. It's that quick. So the energy, the power, so the energy lost per second is current times voltage. And then by using V equals IR, you can get 3 different versions of it. For instance, say I tell you the current running through a resistor and the resistance. Then you're going to use the middle version, I squared R. Say I give you the voltage across a resistor and the resistance. Well, then you may want to use V squared over R. Just use whichever one's the easiest at the time, or just V equals IR, find the missing variable and use IV. Whatever you want to do. They all work, just 3 different expressions of it using that V equals IR. Oh, yeah, clarify, the unit is watts. So if you ever see watts, so for instance, on light bulbs, it gives you the wattage of it. On any electrical device, it gives you the wattage of it. That tells you how much energy that device is going to consume every second. And that's how your power bill is calculated. Is basically they just take how long it was running times the wattage. And so basically the time over the whole month times the wattage, that's how much energy you use. You get billed for kilowatts. And they just do that over the time of the month. So there you go. That's what that means. Now you understand what wattage on a light bulb means. Higher the wattage, the more current it's drawing for the same voltage. All right. This is gone. Where did this go? There it is. All right. What is the power lost in the resistor in the following circuit? Same exact circuit, 5-volt battery, 15 ohm resistor. Use whatever version of the last one you want to use. We already calculated current before, so you can use any of the equations. You have all 3 variables, you get to use whatever you want. Using the word lost because it's a resistor, so it's basically going to heat up. Alright, give you all about 5-10 more seconds. Alright, so 5, 4, 3, 2, 1. Okay. So for the sake of making my life easy with math, so we just said power equals IV. I've decided I want to use this one versus the other ones, just because it's the easiest one to do in my head. We found that current last time was 1/3. Voltage is 5/3. There you go. Watts. Real quick. Again, the reminder here is this is the voltage drop across the resistor, not the voltage of the battery. But if we're saying what's the power lost in the resistor, it's the voltage drop across the resistor. Because for instance, if I have two different resistors in the circuit, they're both going to get different voltage drops. They'll end up having the same current, but so they're going to have more or less power dissipated based on that. More power dissipated if they have a higher resistance. All right. All right. There you go. Another version. What is the power loss in a 10 ohm resistor which has 5 microamps running through it? Something may be off here. Yeah. I'm going to correct some of these values because if you could not find the answer, that's why. Keep jogging through it. Apologies for that. It will pop up eventually. Did I still mess it up? Oops, wrong way. Alright, don't worry about this one. I'll just give you the answer. You can say it. This is what happens when you try to make corrections on the fly. So this is where you need to be careful. So I made this mistake, so I'll clarify the mistake I made. If you all didn't get this, this is secret option. This is A. Just put A. You get a free answer. There you go. So everyone put A, you get a right answer. I'm not going to penalize you for a mistake I made. Alright, so originally I had 250 minus 6. That's wrong. So I'll show you all the answer to this, and I'll tell you the mistake I made, so that way you all can also be careful of not making that mistake. Power equals I squared R. So it's going to be 5e to the minus 6 squared times 10. Which, when I plugged it into my calculator, unfortunately it's the one I don't like to work with, but that's what I got. Watts. What other people also got this? Alright, perfect. So the mistake I made when I tried to correct it is I really quickly was like, oh, let me convert this to the minus 8. And so I ended up going the wrong way. This is actually 0.0012250 e to the minus 8. So I ended up going the wrong way. So this is just something to be careful of on tests. Because it's multiple choice, it may not always be the one your calculator gives you. Make certain you convert your orders of magnitude correctly. Clearly, it is an easy mistake to make. 9, 10, yeah. E to the negative 11 for this one.
Negative 6 times 2 is negative 12 plus 1.
Did I plug into my calculator wrong? No. So you get 10 times 10, or so 5 times 5 is 25. Then you're going to get e to the minus 12. And then you get it times 10, so that's going to bump it to 25 e to the minus 11, which then becomes 2. Even after I've done physics for 9 years, you can still make these mistakes. Please double check your work. The way to check if this makes sense, 2.5 e to the minus 10. That's a small number. E to the minus 8 is a bigger number. I should have therefore made this smaller if I'm increasing the order of magnitude. So that's always just a way to kind of check to make certain it makes sense. Or you can again go backwards. If I converted from this to this, I should have gotten 2 more zeros here. I didn't. So these are all good checks to make because you can make these mistakes at any point in your life. Don't crash. And when you're doing engineering, way more important. Thankfully, all I'm responsible for is your all's learning future. That's not that important, right? That's super important. You all will be in charge of things worth a lot of money. Don't make these mistakes when it's worth a lot of money. You can't really go back and be like, oops, let me quickly correct that as my thing has crashed and burned and whatever may have terribly happened. It's always good to have checks in your system to make certain of that. Oh, all right, this is a good question. I'm going to finish this one and this will be the last of it. This is good because we get to use calculus and calculus is fun. If you don't agree, that's fine. You just haven't done enough calculus. You'll get converted eventually. All right. So very quickly, the question is, all right, settle down. Got a little bit of chatter. Again, I enjoy having you all talk about problems, but I want to make sure everyone can hear. So if we said that current is dq dt, this is just, we have to remember the definition of current. We have Q here as a function of t. So this is kind of going to be, I'm not going to rewrite it, it's right there. I'll rewrite it. 4.00 t to the 4th plus 6. Actually, and this is the fun thing, you got to convert that from millicoulombs to regular coulombs. So this is kind of like in physics 1 where you had a position equation and you had to convert it to velocity. You just take the derivative with respect to time and you get there. So if I do dq, which is a function of t with respect to t, it's just taking the derivative. Derivative of 4 times t to the 4 is 16 times t to the 3 minus derivative of 1 times t is 1. And we actually didn't even need to worry about that, but it was still good to catch that unit there anyway. All right. And this equals current with respect to time. So now all you have to do, plug in 3, because we want to know it at 3 seconds. That's our base unit. So 16 times 3 to the 3rd minus 1 equals 9 times 16. I don't know that off the top of my head. No, 27 times 16, even worse. All right, 431 amps. There you go. So that's a fun calculus version of the problem. I'll do these next, I'll leave this up. I'll leave the next ones for next class. Give you all a few minutes early today. Have a wonderful weekend. If you have any questions about voltage current, please ask me. You need to understand, I say you need to, if you don't understand this, you're gonna have a rough time in the next few weeks. You don't need to understand it now, but you do need to understand it eventually.
Thank you.
No problem, have a good one.
Have a great weekend. Thank you so
Have a good
much.
one.